Hello, I'm Hättasch, and today I'm going to present you our paper, It's AI Match, a two-step approach for schema matching using embeddings. To create value and derive knowledge from data, you have to dig into this data. But honestly, this sample image is much too simple. So in reality, data looks more like this. Data may be distributed over many different systems. For example, customer relationship management systems, web server logs, and even more. And this might be even a harder problem when company, for example, merge the data of different companies or different branches has to be integrated to find insights. Especially there's a problem that this data from different sources uses different schemata. So we need schema matching to find the semantic correspondences between elements of those multiple schemata to then have the chance to integrate this data into one single database that then can be queried. Automatic schema matching can drastically reduce the manual effort needed, and there is already a lot of work in this field. For extensive analysis, I refer to the paper here. So there are in general different ways to match data. You can either just have a look at the table or column names, so you do a schema-based approach. You can also look at the contents of the rows and columns, so you go with the instant-based approach. Some database schemata have natural language comments with them that can also be used to find correspondences between tables and attributes. And of course, you can combine all those different approaches. The first and early schema matching approaches tried syntactic matching, so they only looked, for example, on added distances and tried to find words that are the same or very close to. But as you can see, this won't help. You won't find, for example, that source and origin is roughly the same. But on the other hand, words like house and mouse have only added a distance of 1, although they are quite different. So syntactic matching can only find similar representations, but not same concepts. That is what we're really looking for. So what we want to have is some semantic matching that is able to find not only strings that are same or very close to each, but also different strings that represent the same concept. However, just finding synonyms like this, for example, can be done with resources like WordNet or also with learned models is not enough. We also might want to find matches across languages. Another thing is the support for domain-specific words, as most tables contain domain-specific content. And we also want to make sure that while we on the one hand try to not only find exact matches, but also things that are close to each other, we can on the other hand differentiate between similar but not the same concepts if it matter. For example, in this case, we want not to match actors and directors, even though they only differ in one attribute, and even though there might be some actors who are also directors, but generally speaking they are different, so we don't want to match them in that case. So to go beyond this syntactic approach, but also to go beyond semantic approaches that use fixed and existing resources like WordNet, so to support more domain-specific words, to more support going cross languages, we need learned models. And currently the most popular choice for learned language models are embeddings. So I will now give a short recap what embeddings in fact are. Embeddings represent a concept, a word, by a vector and use the context of that word for that. So they are trained on big text collections and look which are the words that another word usually goes along in the sentences. They use this to map the concepts into a semantical vector space where the position of the vector plays a role, and we can use, for example, the cosine similarity to compare vectors and find out if they describe similar concepts or if the concepts are different. Modern embedding technologies also resolve some problems that assisted with previous approaches, like a very limited vocabulary, by trying to not represent every word with an explicit vector, but only represent the most important words. And for the rest, go with something called word piece tokenization, where you say, like, if the word is not completely represented in our vocabulary, we split it into multiple sentence-bearing pieces. Like, for example, strawberries is split into straw and berries, and just encode those pieces, because we don't want to encode all the different berries, but it's sufficient for our application if we just know it is some kind of berry. And this allows it, for example, for bird, which is probably the most prominent embedding technology right now, to use only 30,000 words in a vocabulary, but cover nearly all English words. So as I already mentioned, there are different kinds of embeddings. So the classic approaches like word2vec or GLOVE just used a left to right method to go through sentences and also encoded words always the same. Elmo, which was kind of the next generation, tried to improve on that and try to include more context. And nowadays we have the transformer-based contextualized embeddings that try to include all context at once and also allow it to represent a word differently depending on its current context, making it much more robust and allowing it to go with multiple word meanings and get multiple representations for that. In our evaluation, we found the Google Universal Sentence Encoder to be most useful for the schema matching task, which can be seen in this experiment, where we tried to compare the representations of different attribute names. And as you can see in the left part of the slide, the similarity of the vectors using the bird embedding technology are quite high, disregarding if they show if you compare similar or dissimilar attribute names. While on the right side you can see for Google use that the range is much higher, so we can better discriminate between relevant matches and irrelevant matches which Google use. So we use that most for our evaluation in the paper. How can embeddings, generally speaking, be used for matching? So you can take everything that is a string, so the table names, the column names, the string instances, and represent them using the embedding. So you get a vector for that. And you can then compare this vector using the cosine similarity. So you determine a value that can be used then, for example, using thresholds to assess the similarity of two vectors and thus two concepts. Our approach now takes those new contextualized embeddings and applies them to the whole matching and integration process. So we use those embeddings on all the different possible matching levels. So we first do table matching to find possible correspondences between two tables and reduce the source space. And afterwards do attribute matching to find the exact matching columns. So this shows our general approach. In both of those matching steps, we can apply different matching strategies. For example, using schema or instance information, which we all evaluated in the paper. And depending on the exact matching problem, the size of the schemata, etc., a manual review can be done between the steps, but also, of course, afterwards. So let's have a look at the first step, the table matching step. In the first step, possible matches between tables are searched for, either on the basis of the available schema, on the instances in the tables, or using both information together. The most simple approach is to go structured base and compare the table titles. And we did some experiments to identify good hyperparameters for this step. You can find details in the paper. The aim here is a high recall to make sure all correct correspondence are passed to the second step. It's okay if we have more than the grade 1, because that just increases the computing time needed a little bit, but we should have a high recall and have all the important correct correspondence included, because all the other possible correspondence are discarded after the first step. And those of you speaking German can see that for English in a German database, where we ran an experiment on, all the correct correspondences were found in this example, but also for other correspondences, because we forced the system in this setting to give us the 5 best correspondences. Another possibility to compare tables is by their instances. So the general idea is that 2 tables are similar if they share similar columns. And to check this, we can represent the full columns by vectors and then find the closest columns in another table. This might require sampling. You can find details in the paper. And of course, again, you need to have thresholds here, which depend on the matching task. For example, if you want to have exact correspondences, then you need to have most of the columns to have a corresponding column in the possible matching partner table. But if you want just overlapping tables, it's okay if there's just a small amount of columns that is shared between 2 tables. We did some experiments to also test this strategy, which you can find in the paper. And we also combined the 2 approaches, the instance-based and the structure-based approach, and found this combination to be the best among our approaches. Let's have a look at the second step, the attribute matching. Again, as I said, this matching step is run independently for each of the table pairs that were identified in the first step. And since we already know that there might be a correspondence between them, we can spend more time on assessing each of those. Again, it's possible to use instant-based but also structure-based matches. We had short experiments on comment-based matches, and also this can be combined. The big evaluation we did for that takes 2 approaches. One is a structured-based approach that compares the attribute names using embeddings, and the other one is an instant-based approach that compares the vector representation of sampled columns. And we compare this to 2 baselines from the Coma Plus framework by Do and Ram, which includes many of the relevant matching approaches that were researched during the last years. One of the baselines is a name-only approach that just looks at the titles of the tables and attributes, and the second, more complex one, takes those names but also instant information. And we applied our approaches, but also the baselines, to a dataset that concludes of the 38 problems of the ontology alignment evaluation innovative benchmark that contains at least some kind of instances. For the first 23 problems, we have measured for all the 4 strategies the precision and the recall, so how many of the returned matches were correct and how many of the existing real matches were returned. And you can see that for the first 23 simple problems, which contained renamed tables and attributes or partially changed structure, but not everything at the same time, our approaches both have a higher precision than the baselines, And the structure-based approach also has a higher recall. When we now look at the remaining 15 more complex problems where the names and the structure changed, we can see that the baselines and our name-based approach have a very low precision and recall here. But we can also see that the instant-based approach has a very high precision and it has a recall of about 1/3, which at the first moment sounds a little bit low. But when you know that only 1/3 of the tables have instances at all, this means that nearly all the correspondences were found. So our instant-based approach was able to, using those instances, find nearly all matches. So if we take those both together and see for both of them which were their part where they work best, you can see that they would outperform the baselines. So in the future, we want to have a further look at pre-processing the data. We also want to look if we can fine-tune the embeddings to get even better results. So to either adapt the resulting vectors after they were vectorized using additional information, or if it helps to retrain the embeddings with text corpora, for example, containing the domain-specific words from the domain of the table we tested on or we used the system on. Of course, also numeric features could be used to assign the matches. And also we had only a short look on the natural language comments, which are included in some databases. There could be further experiments. So to conclude, we can see that embeddings can be used for schema matching, both structure-based and instant-based. They can be used standalone, but we suggest to use them in addition to existing matches, which is also the way it's normally done. And we suggest to use those modern contextualized embeddings. And we also showed that our two-step approach can increase the precision and the recall of the system. So thank you for your attention, and I'm interested in your questions now.